or the commoditized hardware controller, with the programmers at those companies then choosing how to write and implement the control plane at the controller as opposed to using something that's off the shelf logic. So, but yeah, it is an interesting idea, but you can't just take OSPF out of Cisco IOS because Cisco wouldn't let you. But there were some open source OSPF implementations that I talked to a few people at trade shows, and they said, yes, we know that, say, Google Compute is using our OSPF as the basis for what they're working on for you. So AT, you had asked about the API that Puppet, Ansible, and Chef are using. Well, Ansible, but they also use one called NetConf, which is a shortened word meaning network configuration. So it's a protocol that we don't actually cover for CCNA, but it's a way to make a TCP connection into the device and pass structured data. And what I mean by that is it's variables that are easily described by a program, not so easily read by a human, again, optimized for program. But it can then describe the configuration that you want loaded into the device. It also has data about status, show command equivalent, if you will, that you can extract with NetConf as well. So those are the main ones. So SSH and NetConf are the main ones with Ansible. Puppet, I think it's only SSH today, but it might also have NetConf that I just haven't heard about yet. But I don't watch Puppet as much because it's just not used nearly as much as Cisco gear. All right. So the first of these we'll talk about is where, how I said Cisco said, all right, we don't embrace the open flow controller idea that first came out from that Project Clean Slate. They did some, but it was clear they were not embracing it across the product line. They said, we're too big a company to do one thing that's SDN everywhere. So in each of their product areas. And what they did in the data center is something that you might have heard of called application-centric infrastructure, or ACI. So here's the idea. There is a controller that's represented by a yellow rectangle here. And here's our data center down at the bottom. And there's the southbound interface from the controller there. And up here is us. And we can interact with a GUI or an API. It's a REST-based API. And one of the key points here is that if you can do it with the GUI, you can do it with the script, you can do it with the GUI. And in fact, if you use the GUI, all you're doing is clicking, and the controller is then creating an API call to do something. So it's functionally equivalent between the GUI and the API, always on purpose, which is a great approach. You could also have a Cisco or other vendor app that understands this northbound interface that gives you yet another API. Let me give you an example. Build a private data center with ACI. It's got a controller. You've got a VMware cloud application that builds a cloud catalog for your private cloud. It could interface to your ACI design and manage your ACI system, move your VMs around, because VMware has been in that business for a long time, as an example. All right, so a lot of options for what goes on here. Now, the physical connectivity is different, and I mention it because of this phrase is part of the CCNA exam topics. So here's the deal. You have some switches, and those switches have a role of either a spine switch or a leaf switch. Leaf switches are where the servers are connected down at the bottom. Spines never connect to an endpoint. Every leaf connects to every spine connects to every leaf, but you never connect spines to each other, and you never connect leaves to each other. You might say, huh? That is a spine-leaf topology. And the goal, part of the goal here, is to have a very predictable network topology. One of the reasons, for instance, that spanning tree exists is that it's any topology. Well, this spine-leaf topology, sometimes called a Clos tree, named after the fellow that came up with it. His last name was Clos, C-L-O-S, is that you have a predictable topology, and if this is where my servers sit down here, every server is 2 hops away through every spine. because of this topology. Here to here, come up here, middle spine down, 2 hops away, left spine and down, right spine and down. So the paths through the network in the data center are very predictable. So we can take advantage of that for how we forward traffic in this network versus saying, hook up your switches any old way and we'll figure it out. Let's constrain things because we want predictability. So that was one thing Cisco did with ACI. By the way, they had people left Cisco knowing they were going to go create this and that Cisco would buy the company back later. All right. They call it a spin-in in the business schools. So here's you get a lot of these, the compute system from Cisco, where each of these big boxes is, a server with a hypervisor and a vSwitch and a bunch of VMs. You have boatloads of those, maybe a few physical servers. Somewhere in this network, you'd have one APIC or maybe a 3 APIC cluster if you're large enough to want some redundancy, and maybe a few routers that give you a path out of the network. But lots and lots and lots of server hardware that's virtualized. So that's what you physically got in this new ACI world. But somewhere in there is this APIC controller. But that's not what it's really about. Application-centric infrastructure, remember how I said the controller, it does these complicated southbound things, and it also gives us really easy-to-consume northbound APIs that don't just make it easy to do old-style stuff, but it gives us whole new things that we couldn't even have done before. This is a great case of that. You don't configure OSPF. You don't configure spanning tree. You configure intent based on application. So let me give you a quick word about this. So an application that you and I think of as a web server, there's actually 3 parts to it. There are servers that are reading and writing from a database like product database. You go to Amazon and look up my book. Amazon's looking in a database of all their books, for instance. There are application servers. These are servers that, for instance, say, hey, web pages are dynamic. We know that I'm going to show different ads to one user than another user. How did that happen? There's an application that looks at your spending history and your browsing history at that web page and chooses what ads to show you, right? Well, the application processes that data. The web server is the one that actually sends and receives the web page, sends the web page to the user, connects to the user, sends the web page to the user. So there are actually 3 kinds of servers in a typical web application. So keeping that background in mind, by the way, the web server needs to communicate outside through the router to the rest of the network to reach the user, right, to get the packet to the user. So what ACI says is that northbound API says you can identify some devices as being external, meaning routers, and some as web servers for this application, and some as app servers for this application, and some as database servers for this application. And by the way, app servers talk to database servers, and web servers talk to app servers, and web servers talk to the routers, but you don't need the database server to talk to the router directly. So that's not allowed. The only thing that's allowed are the policies that are explicitly stated here. I just talked about things we've never talked about. Not OSPF, not spanning tree, not MAC address learning, not de-encapsulation and re-encapsulation. This is what you configure at the northbound of ACI. You can do it with the GUI. You can do it with the API. You tell it, this is my intent. We call it intent-based networking. And what happens? Well, we tell the APIC that at northbound, it's got a seldom mentioned southbound API that uses a protocol called OpFlex. There is a distributed control plane, but it says my intent is this. The control plane figures out what that means for forwarding. And the only forwarding entries that are created are ones that allow the policies that are explicitly stated. So it's a whitelist approach, if you've heard that. Whitelist meaning the only forwarding that's allowed are the ones we defined. Everything else is disallowed, right? So by definition, it's more secure. We're not allowing all, and then having to use access lists to prevent subsets of that. So unless we tell you by policy we want a pass to happen between endpoints, it doesn't happen. That gets implemented. The data plane only has entries between the endpoints that the policy state, and things get forwarded to the network. It's cool stuff. So how does this all work in real life? Well, you could still sit at a GUI with the APIC and make it all work. And eventually that works, but eventually you do it 300 times with the GUI and you say enough is enough, and you borrow a script from somebody and you change it to meet your needs, and you use a script to create 100 at a time of whatever you're doing of these little applications. There can even be software from other companies like, say, VMware that I mentioned. It talks to the APIC. It does the same thing. For instance, you interact with your, cloud software from another vendor, which then talks to the APIC, which then implements what's going on. All right. So that's one example of an SDN controller-based implementation from Cisco. I'll tell you about another one here in just a second. I'm going to check the queue. Broader logic base. I haven't played with it. I've just read about it. But I would say Ansible, but broader set of capabilities. All right. So if ACI was Cisco reimagining data center networking, then SDA, let me back up, software-defined access is Cisco reimagining campus networks. Campus networks, that's where we kind of spent our life here for our 4 days together. So what did they do to reimagine? Well, they put a controller into the picture. This is our campus network. The details are unimportant there, but there's a controller. You've got the GUI. You can use scripts to interact with it, programs. The GUIs and the scripts are functionally equivalent. If you make a GUI call, the GUI is generating an API call under the covers. Other apps can interact with the API as well, so on and so forth. Same idea there. Now, what's happening in SDA is unfortunately way more complicated than what CCNA requires of us. I would rather they had either ignored it for CCNA or committed to it for CCNA, to be honest. So I've already got a to-do to see if I can find a way to simplify with a few extra drawings here. Let me just make a point. Think of an access switch with a bunch of desktop computers on it. And we've got some distribution switches up here. And imagine a bunch of access switches down at the bottom. We could simplify logic. Remember how we had that spine leaf design where we used a specific topology to simplify logic? Well, if I knew that all my potential destinations were somewhere up here on the other side of the distribution switches, if I knew I always had a link to every distribution switch from my access switches, anytime I wanted it, and I could count on it existing, then great, that might be an advantage. If I could just know that there's always an ability to send over one hop, if you will, in my switch network, a packet to the distribution switch, and the distribution switch would know how to forward it outside of the campus to the router and the rest of the WAN. That would be maybe an easier approach to life, all right? And that's kind of what SDA ended up doing. So let me back up to the slide here. So here's the idea, tunnel. And that tunnel uses a tunneling technology called VXLAN. But what I want you to think about is that a message comes in here from the left, and it gets encapsulated in an IP packet. It gets delivered over to the egress switch and forwarded out to the destination. Right? That whole idea of, hey, you can count on always being able to one hop away, logic-wise, one hop away, that distribution switch that's the edge of the campus, I can reach that. So we call that the overlay, this set of VXLAN tunnels between each pair of switches as needed. It doesn't have to be ahead of time, but as needed, you can always have a tunnel between any of the switches on the edges of the network. Underneath that, though, in order to create connectivity to support that VXLAN tunnel, you can have any old switch topology you want to. They can be layer 2 switches, layer 3 switches, as long as they support IP. As long as you can get an IP packet from here to here, your underlay is good. All right? So it's like you've got 2 layers of network. An underlay that's just there to support the forwarding of IP packets in the campus, and a bunch of overlay tunnels. So it's kind of a weird thing to get used to. So here's a slide that just formalizes what I've been talking about for the last minute or so. Overlay is the mechanism to create and the set of VXLAN tunnels between the switches that we use to tunnel traffic from the edges of the network to the other edge of the network. The underlay is a bunch of network devices that let you forward the packets in those tunnels. And the fabric is the combination of those 2 things together, but more often it actually refers to the overlay, but it really is all of them together. All right, so some terms. The fabric edge node connects to endpoints, not routers that get you out to the rest of the network, but truly endpoints, like the access layer, all right? Water node, it connects devices like routers that connect you to the rest of the enterprise. So think access, think distribution with those first 2 terms in terms of similarity. And the control node is doing some of the overhead features that make all this work. In particular, it uses a protocol called Lisp in order to figure out how to set up these tunnels. So that encapsulation that I mentioned, you take a frame coming in from the left from an endpoint device like this PC, and if it's fabric edge node, meaning it's connected to endpoints, we take that LAN frame, the frame now, we don't switch it like a LAN switch. We encapsulate it in an IP packet, which actually has some other headers in here as well that turn out to be very useful, and forward that packet to the egress fabric edge node, where we can send it to that destination if it's another endpoint, or if it's a router, we can do that. All right. You get with it. And one of the things that's pretty cool about it is this. You've got this controller. It's called the DNA Center controller, by the way. And you've got your network. And by the way, you see the southbound APIs down here, include NetConf and RESTConf, which I guess was in one of my answers a little bit earlier. But one of the features you can get is when the endpoints connect to the network, you can then require of them an authentication process that identifies them. And so what we can do with this controller then is to say, I'm going to create some policies that say which class of devices can talk to which. And it's a very simple thing to compare. Again, controllers, because they're written by professional developers who want us to use their controllers, can give us some great features in their APIs that help us build better networks and operate and scale and spend less time to achieve what we're trying to do. And for instance, we could set up a policy with the GUI or with the program that says, hey, when an endpoint identifies itself as an employee, we permit it to connect with devices that are identified as internet, i.e. a router that connects to the internet. Or if it's an employee, they can connect and send packets to a device that's identified as a partner, or a user that's identified as a partner. It's based on the user authentication, by the way. But if an employee wants to communicate with a guest, we just don't allow it, right? So that kind of a policy in this little table and a slide is pretty easy to understand, right? We don't want guests to communicate directly with anybody else. What should guests be able to do? Guests should be able to use the internet, right? That's what we want to work, and nothing else. So these are some pretty obvious business policies. So rather than have all these complicated access control lists, we just say, all right, we're going to require everyone to have an authentication process. We'll identify employees and partners and guests. This will be our logic for what's allowed. We've configured that, and the network does it. If you're waiting for me to make it more complex, it's not. Yes, there's more work to do. It uses ICE for the authentication process, but it dynamically adds whitelist entries to who can talk to whom, and then it won't let the guests talk to others because there's no forwarding entry for them. There's nothing to match to allow the forwarding for, say, a guest to talk to an enterprise's device. So it's pretty cool stuff. It's gaining some traction, but there are parts of it, like there's a lot of good operational data that comes out of it that just listening to others that live it every day seems to be pretty popular. All right. So just a few more things here. I'm just checking on my timing. Bear with me. Yeah, let's at least do REST. I usually skip JSON because it's really easy to pick up from your own reading. But REST is a pretty important concept. So here's an idea. These APIs on the northbound side, they almost always follow a convention called REST. They're different APIs, but the style of API is called REST. Representational State Transfer. And REST uses a protocol we know, uses HTTP or HTTPS. And so what happens with a REST client, so this is the program you could write or somebody else has written and it can run on your computer. It sends an IP packet over to a REST server. And that packet, IP, TCP header, HTTP or HTTPS header, and it's got a verb. Now, if you instead think of a web browser on the left and a web server on the right, it's very similar. I mean, it's the same protocol. And when you want to get a web page in your web browser, you're going to send a message, and the verb is going to be a GET request. Get this web page. We even talked about that some, I believe, on yesterday. Right? But that HTTP message is going to have a verb like GET, and it's going to have the URI inside the header as well. And that message is going to get over to the API, and the API, they're ready to get that request and send some kind of a response. Right? So the response is going to come back, and it's going to have a response code, not a return code, by the way, it's a response code, and have the data in there. And if it's a lot of data, it'll have multiple messages that TCP will reassemble into the original and sent by the REST server. So the REST server, the people that made it set it up ahead of time so that there would be data available at different URIs. Very much like a web server, the person that created the website has created a bunch of web pages that would be available at different URIs. So how would we in a program request data? Well, we'd use the URL or URI path, that is the resource. That is what happens after the host name. And there are things called URL parameters. Those happen after the question mark. Those happen after the first single slash. And then there's actually HTTP header fields that you can use. So let's work through that a little bit. So here's a URL or URI, and the path, aka resource, starts there after the host name. And the person that, or the people that made the API, they said, all right, ahead of time, DNA, intent, API, v1, network device represents something, some data. And by the way, you might guess this is part of the DNA Center northbound API. Alternately, you could make a call to the northbound API of the DNA Center and have that same path followed by a question mark and text like this. Now, this is generic text in the back, but you could have different variables. And the API creators, if they had created a variable named farm1 that would have been an IP address, they'd be ready and watching for that. They're more likely to have created an IP address variable name, right? So it's got to match up with what's in the API. How do we know? Well, there's API documentation. But there's a bunch of URLs, a bunch of resources predefined by the API creators, and a bunch of query parameters, variables that can be specified. So if we just make this get and we reference a URI that's generically called URI number 3 in this example, here's URI number 1, number 2, number 3, number n. And so the REST server is going to pick this one because it matches the request and return it back. All right? So not a terribly complicated idea. So how do we know? I mean, we didn't make this stuff up. The API creators did. So you could go to the DNA Center documentation, which you can find at developer.cisco.com. That's a site known as DevNet, and that's where Cisco keeps a lot of their programming-related documentation. And you can find the DNA Center documentation. It'll include the API documentation. It might be hard to read on your size screen. It's a little small on mine, and I've got a 24-inch display I'm writing on over here. And that's the same resource name in the prior couple of slides at the top. And down here at the bottom, it tells us the data that will be returned. And this is in JSON format, by the way. So we know what kind of data to expect. All right? So we can look at that, and that's how you learn about an API. In fact, there's a button oftentimes that will let you see how to make a call with that API. All right. So the REST request with the header field. So you've got the resource, the stuff after the slash. You've got parameters after the question mark. And HTTP header also supports some header fields that you can use. The header fields are things that are common amongst HTTP requests across APIs, not just networking APIs, because they are defined in an HTTP standard. The resource and parameters, each individual API gets to make that up. But for standard things, you can see those in the HTTP header. Here's a copy of a screen from the Postman application, which is a very popular API tool. And for instance, authorization, a way to get authorized to use the app. We can plug a value in there to specify the content type as JSON. There's a code you put in there. These are things that are actually stored in the HTTP header. So 3 places: the header, the resource path, and the query parameters. Last little bit on REST, and I think then we'll need to transition to the final bit. There's an acronym called CRUD that you'll see mentioned a lot, and it represents create, read, update, and delete. And those are the 4 main actions the program does. Create data that represents something, update it as time goes on, read it to see what the current status is, and then delete it when you're done with it. For instance, in ACI, creating an endpoint group of routers, an endpoint group of web servers for some app, application servers for some app, and so on. Each of those things will be represented by data that you would have an API call that created. Later, if you want to know the status, you'd read it. If you're done with that app and want to get rid of it, you delete it, and so on. So you want to be aware of the CRUD actions and also the HTTP verbs. So GET is the one we all know because you're just reading, like reading a web page in the web model, reading the API to get data in the API model. Delete's pretty obvious because it matches the delete verb in HTTP. The ones that aren't so obvious. To create something, you would, for instance, use a post verb, as it turns out. Then update, you could use these 2 HTTP verbs, patch and put, which are typically used to update something. All right. I will leave the JSON short section if you're following along with the PDF of the slides on your own. The book, I think, spells it out pretty well. And there are lots of great tools for learning JSON. And my timing says we need to move on to, let's see.